So okay, we are here now, right? So this is phase diagram for copper nickel. Phase diagram for copper nickel. Now, as I always tell you, don't get worried about, oh, this is a new complicated thing. This is just new. There is nothing complicated. We will go step by step, and you will see that after a few minutes, you will feel, oh, I know it very well. So let us see now. Let us see. What is the vertical axis? It is the temperature in degrees Celsius. What is the horizontal axis? It is the composition. If you remember, there was one thing bad about chemistry. They call it weight when it is actually mass, right? This is weight percent nickel, but actually it is mass percent nickel. But because in earlier chemistry they used to call it weight percent, so we still call it weight percent, but technically it is mass percent. So it is the composition. If you see it here, it is copper, here it is nickel, and it says weight percent nickel. So when we are here at 40, it means it is 40 weight percent nickel. So whatever alloy we have here at this point has 40% nickel, and that means 60% copper. If this is the alloy we are talking about, then it has 80% nickel, so it will be 20% copper, right? So that is it. So when we say 0% nickel, it means we have 100% copper. So at this point we have pure copper. And when we say 100% nickel, then there is no copper. So the two ends are the pure materials. This end is 100% copper. This end is 100% nickel, right? And this is the temperature. This is the temperature. If you now see, we have these two lines, these upper line, this upper line and this lower line, which are the pink or the purple lines. Above this upper line, the metal is completely liquid. And below this lower line, it is completely solid. So this is the most important thing. This is the most important thing to remember. Whatever you see, we take 40 gram of nickel and 60 gram of copper. So we will have this material, right? 40% nickel, 60%. So 40, if we take 40 gram of nickel and 60 gram of copper and melt it. So when we mix them together, they are together, say there was, and we have melted them and we keep on increasing. So if we go to something like 1400 Celsius or 1500 Celsius, then we know that the mixture of this 40 gram of nickel and 60 gram of copper has completely melted, right? So this is it, that we take any. So it means that if we are here, then we start with say 20 gram of nickel and 80 gram of copper. So any point here is a different alloy. Any point here is a different alloy, right? So we have hundreds of alloys here. We can take it. We can take this point. This point means we have started with say 10 gram of nickel and 90 gram of copper. We have mixed them together and then we are heating them. So now they are liquid. They are completely mixed together. We will now cool it, and once we have solidified it, we have 10% nickel solution, right? We have 10% nickel alloy. 10% nickel means 10% nickel, 90% copper. So there are lots and lots of different alloys here, right? Any point that we take, we can do the other thing. Okay. So when you are here anywhere, so let us take lots of examples. We have say 30% alloy. It means 30% nickel, 70% copper. If you heat it, then you need at least this much of temperature to become completely liquid. If you have 80% nickel alloy, then you need to go at least here to make it completely liquid, right? So now this upper line is not called a liquid line, we call it a liquidus line. Liquidus line. We will tell you why. Similarly, this line below is called the solidus line. So above the liquidus line, anywhere above this liquidus line, the material is completely liquid, and below this solidus line, the material is completely solid, right? So that is it. Now if it was one material, if it was only copper or only nickel and we melt it, then we will say this is liquid. But when we have a mixture of the two, then there will be an issue. Because we have seen earlier that if you mix the materials, the two of them have different melting points or different freezing points. You have complete liquid, but these are two materials inside now. So when you start cooling them, first one of the materials start to freeze or starts to become solid, but the other material is still liquid. After some time, when the temperature has dropped further, we go to the freezing temperature of the other material. So now that other material starts to freeze, isn't it? So therefore, it is not that the whole material will freeze at one constant temperature. One material will start to freeze because it has a higher freezing point. Then as the temperature keeps on dropping, some of the material has converted into solid already, but the other freezing point now is reached, and then the other material starts to freeze. So therefore, there will not be a simple liquid line, there will be a liquidus line, and so on, right? Now here we are saying that, you see, this is 50, suppose this is 50, this is 60. We take a material of any composition in between. Can you read what is the material? 53 weight % nickel. So this is an example now. That as an example, we are saying that we have taken, suppose, 53 gram of nickel, which means 47 grams of copper. We have mixed them together and we have heated them until they become liquid, right? So again, remember, 53 weight % nickel is our original composition. So what do we want to find out? That when we take any alloy of a given composition, melt it completely, and then start to cool it, just like we will do in a refinery of a metal, like a steel plant or something like that. So this is a plant where copper nickel alloy is produced. So if we initially take 53% nickel and 47% copper, and then we melt them completely in the furnaces, and after that when we try to cool it, then what will happen? That is what this phase diagram will tell us. So we will try to find that out. So the question here is, with this example, that when we take this material, 53% nickel alloy, and we are cooling it, and we have cooled to 1300 Celsius. Then we want to find out the details of the alloy at that, right? We have heated it, melted it, so we are, say, at 1500 Celsius or something like that. We started cooling it. But when we reached a temperature of 1300 Celsius, then we want to find out. So this is the question. Remember, this is how the question will always be, that we give you an alloy composition. So here the alloy composition is 53 weight % nickel, 47 weight % copper. So this is what we give you. Then we give you a temperature, 1300 Celsius. So these are the two given things in the problem. I always tell you, right? The problem is about studying the phase diagram. If we want to study the phase diagram, first of all, we will have to give you the phase diagram. So if I want to ask you about copper nickel alloy, then this phase diagram is given to you. Then in the question they say that the initial composition, the original alloy that we are asking you, is 53 weight % nickel, which automatically means 47 weight percent copper, and we give you a temperature of 1300 Celsius. Now they say, now tell us that with this, what else can you find out? So what will be the first step? We will make a horizontal line at this temperature. We will make a horizontal line so that it cuts the liquidus and it cuts the solidus. Right? This is one thing that we will do. This is not the first thing, actually. I'm sorry, this will be the second thing. The first thing that you do is that you mark the composition, 53 weight percent nickel, and you make a vertical line. See, because this is where the problem started, that what is the initial composition? 53 weight percent nickel. So take out your ruler, take out your scale, and make a vertical line at this. You can extend the line here, does not matter. And the second thing is that what is the temperature? So draw a horizontal line which cuts the liquidus and the solidus and your line, right? So you have now one vertical line here and one horizontal line here. This is your starting point to solve this type of a problem. Okay. Now this line, this horizontal line, if this horizontal line is between the liquidus and the solid, right? You see, this is the solidus, this is the liquidus. So the portion of this horizontal temperature line which is between the two, liquidus and solidus, this portion is called a tie line. So this is just a name. You see, this is a horizontal temperature line. You give any temperature, you draw a horizontal line, this is the temperature line. The portion of the temperature line which is between liquidus and solidus, this portion is called the tie line. So you see, you have learned three new words already on the phase diagram: liquidus, solidus, and now tie line. So now this temperature line cuts the liquidus at this point, isn't it? And it cuts the solidus at this point. So the next step is that wherever it cuts the liquidus, draw a vertical line, and wherever it cuts the solidus, draw a vertical line. So you draw this vertical line and find out as accurately as you can. You can try, you will be slightly approximate, but here we are giving you the exact one, that this cuts here at 45 weight percent nickel. So note this down, 45 weight percent nickel, right? The horizontal temperature line, where does it cuts the liquidus? At 45 weight percent nickel. The horizontal temperature line, where it cuts the solidus? At the solidus at 58 weight percent nickel. 58 weight percent nickel. So we started with a material which had 53 weight percent nickel, and the question is, at 1300 Celsius, what will be in that material? You see, at 1300 Celsius, there will be, you see, if you cut this line, this vertical line and this solid line, then they cut here, isn't it? So it means there will be some liquid and some solid. If it was here, it will be pure liquid. If it was here, it will be pure solid. Anywhere in between the two, you see liquid plus solid. Now the solid here is, solid alpha. We told you that once it solidifies, anywhere here, this solid has the same crystal structure, we call it alpha. So that is why it is isomorphous. That once it completely solidifies, here, anywhere, wherever it is, it has the same solid